In this screencast, I want to talk to you about generalist and specialist species and the implication that has on what we call survivorship curves. I mean, look at this panda bear. Isn't that just the most adorable thing you ever saw? How can they be so cute? Okay, so let's talk about what a specialist species is. So, a specialist species, these are ones that have evolved over time to fill a very, very specific niche in their ecosystem. So, they're super specialized to this one particular food that's accessed in a certain way. They live in a certain place, and like in a tree or in a cave, or they're just very specialized. They might have camouflage as a particular way, or they mimic another species. So, they're very uh, evolution has made them very, very narrowly defined in terms of their niche, but they're really good at that one thing. So examples would be like koalas. So koala bears live in these eucalyptus forests of Australia. Eucalyptus trees have this odor to them because they produce this natural toxin that most things can't eat without getting sick. But they have this natural adaptation that lets them eat it. So they're very specialized to eat just eucalyptus. Pandas, everybody loves pandas. Are from this one particular type of area in China in the foothills of the Himalayas, and they're adapted to eating this one particular type of bamboo. Most things can't eat the bamboo, but the pandas have a special adaptation that lets them digest it. The Canada lynx, look at those feet it has. It's an amazing animal. Look at how weird it is. It is totally adapted to dig in the snow to get at things called snowshoe hares that are its main prey, which are ones that often burrow into the snow. So it's specialized to hunt this one particular prey item, but it's not specialized to wouldn't do well in most other environments. So that's what we mean by a specialist species, highly evolved to a very, very specific niche at which it is really, really good at surviving in. Now, how do you get these things? Well, it takes a very, very stable environment, an environment that doesn't fluctuate much, that stays the same for a long time, so that generation after generation of natural selection can just hone it down to one particular narrow set of traits that makes it ideal for this one particular niche. So as long as the conditions remain constant, these specialist species, they just rock. Okay, like you can't outcompete them. Unfortunately, though, if climate change happens or some other change in the ecosystem occurs, they're so narrowly defined in terms of what their niche is that they tend to go extinct really quickly. So if we look at the species that are, I'm sure you've heard about the problems of species going extinct on our planet. Well, a lot of these are endemic species that are found on like islands or rainforests. So they're only found in one place, and they tend to be very, very specialized. They're highly specialized species, so that when the environment changes, there's just not time for them to adapt to a new set of circumstances. So as long as it was stable, it was great to be that specialized because it made you really able to outcompete everybody else. But the price you pay is if the environment changes, natural selection just takes too long to alter your traits, and you just go extinct instead. And then there's generalist species. So a generalist species, it takes the opposite approach to survival. So generalist species are ones that have they're adapted to a very broad set of conditions. So conditions change, they do just fine. I was eating this, I'll eat that. I was living here, I'll live there. So these things could even live in urban environments. So like if you go to India or most places in Southeast Asia, Thailand, Malaysia, you'll see monkeys, or at least you'll see like gray macaques. You'll see them in city environments because you know what? They're a generalist species. They can live there. In the United States, raccoons, man, you see these things all over cities. They come into people's yards. They just they get into people's garbage cans. They're just a real annoyance. They can totally live there. Coyotes, I'll tell you a story. I'm not going to do it on YouTube, but there's a story I have about the neighborhood I lived in and still own a house in. Coyotes come through our neighborhood, and they eat cats like crazy. So they are just able to adapt to changing environments. So when, like for instance, a specialist species, if people go in and build a housing development with specialist species, they just go extinct because they can't adapt to change. But a general species, like, okay, now instead of eating this one thing that grew in the forest, I'm just going to eat the cats in this person's backyard. So why are generalist species able to do this? Well, they tended to, instead of evolving in stable like rainforest or reef environments, they tended to evolve in the edge of biomes. So in places of fluctuation, so like the boundary between, say, a forest and a grassland, or a grassland and a desert, or a tundra and a boreal forest. They are boundary creatures. That's where their habitat that they evolved in is. So they being able to deal with changing conditions is an evolutionary advantage in their case. So when things change, they do okay. So like like a raccoon, it's like normally it's evolved to eat, like, say, different things, including, say, fish out of a stream or berries or whatever. Now you build a housing development, it's like, all right, fine, I'll get into your garbage can, eat the trash there. So they're able to switch their mode. They have such a broad niche that it can include people's yards. Special species could never do that. All right, so now, in addition to that, let's just talk about the reproductive approaches. Okay, so there's two different approaches to having your descendants survive. Okay, option one: have a whole bunch of babies at a time and just hope that some of them survive. All right. So for instance, that's what our selected species do. They tend to have, like frogs. They'll have 100, maybe they'll have 1,000 eggs. All right, and of those, maybe 10 of them will survive. Being, like by the time they actually turn to little froglets, 10 of that 100 made it. Okay. All right, now there's another strategy, which is just to have like one or two offspring at a time, but invest energy in protecting them and nurturing them and teach them how to adapt to their niche. So if you invest in nurturing the child, it's more likely to survive. So you don't have to have as many. So case like this species, specialists, they tend to have a fewer number of babies, but then invest time and energy helping those babies grow and survive. So you don't have to have as many if you're willing to invest in their survivability. So let's just look at some of the traits we would associate with our selected species. Okay, so on our selected species, again, I should point out. So I skipped over that. When you have this strategy here, we call that an R selected species, and what that means is that you are going to have lots of offspring, and not invest any effort in trying to raise them, and just, if you have enough, some of them by random chance are going to survive. K selected, and we'll see why the terms are R and K in a later lesson. K selected species, those are the ones that are ones that invest in their offspring and just have a couple of them. I forgot to say R and K is kind of an important thing. Sorry about that. Okay. So what are some of the characteristics we notice in our selected species? Well, they tend to not be very large. They have low body weight. They tend not to live very long. Like I said, they have lots and lots of offspring every time they reproduce. They are able to mature very quickly without any parental support. So they very quickly go from being like babies or larvae into adults, and they don't need any member of their species, any parent to show them what to do. They just do it on instinct. They tend to reach their age of reproduction very quickly, like within a year or so, or less even. And most of the time, these are generalist species, almost entirely generalist species. So, like think about like fish species, like herrings, that they within a year they're already reproducing. They occur by the billions. The parents don't spend any effort trying to raise them. Grasshoppers, dandelions. Mice are a little bit on the boundary there, but mice tend to have a lot of babies. Yes, they do feed them milk, so they're investing a little bit of effort in raising them. But as soon as these little guys are moving around, they pretty much leave their parents and figure things out on their own. They're not being trained how to go and hunt. Mom is not investing a lot of time raising them. Now let's talk about K-selected species. So a K-selected species, they have these traits. First of all, they tend to be larger. Like the sort of macrofauna we think of, like lions, gorillas, whales, horses, humans, elephants. They're big animals for the most part. They have long lifespans like we do. They tend to live decades. Uh, it takes a long time for them to gestate. So from the time of conception to the time of birth, it can be a long time. Like for humans, it's 9 months. For some case like the species is even longer. Okay, they tend to have very few offspring at a time. So in a brood, so they'll have like one or maybe two, or maybe a few more, but not many. They tend to have a very small number because Uh, the young are very slow to develop, so they are born unable to take care of themselves, and so the parent has to take care of them and help um, show them how to fit their niche. They be trained, like, here's how to hunt, here's how to find food, here's how to hide from prey. So they have a lot of input from their parents, but because the parents are investing in them, they're more likely to survive. And we typically find that case-selected species tend to be specialist species rather than generalists. So the last thing I want to talk about with this is what's called a survivorship curve. And so basically what it does is we can have different things on our axes, but this axis is always going to be basically time or age, okay? And this axis is basically going to be an indication of how many of them are alive or what percent of them are alive. I'm not sure why this particular one I grabbed starts at 80, but ordinarily we start at 100. And so the idea is at 0 age, most of them are going to survive, I guess. And this is for like rhinoceros, I guess. Like it looks like maybe 15% of them die at birth. Okay, but anyway, so once they're born, what happens is, with each passing year of life, what percentage of them remain alive? So in this case, after 8 or 9 years, 60% of them that are born are still alive. After 16 years, like over 50% of them are still alive. After 26 years, like 45% of them are still alive. But then what happens is they get to there's a certain age. I'm at that age now for humans when all of a sudden the survivorship starts to drop. It's really weird for me. I mean, I'm at the age where like friends I know are starting to die, but for most of my youth, of course, that wasn't the case, and that's because we have this type of survivorship, we humans. Okay, so ours is a little bit better than rhinoceri because we tend to go on until about 100 or maybe in the 90s. Okay. Now, there's different types of survivorship curves. Maybe you could see this coming. K and R selected species tend to have different survivorship curves. Now, before we talk about that, I just want to say that we could put different things. Okay, so on the x-axis, instead of just saying what the lifespan is, so especially we want to compare two different species. Okay, what we often do is we put percent of maximum lifespan on the bottom. So we just say this is 0% of your lifespan and this is 100% of your lifespan. So for a human, this might be 95 years, whereas for a squirrel, this might be 6 years, and for an oyster, it might be 3 years. Okay, but we put them all. This is 100% of your expected, like your maximum potential lifespan. If we don't make this axis percent survivability, then what we're going to do is we can put the total number. But if we put the total number, especially if we're going to bring in the things that have an R-selected strategy, that there's a lot at first and they die, we tend to use a logarithmic axis. And we do that so that we can see what's going on here with these guys. So those are two ways you'll see these things presented. All right, so we come down to three different shapes, okay? What we get is what we call type 1, which looks like this. It's very flat, and then it drops off steeply. We have type 2, which is pretty much a constant linear drop in survivability. And the other type 3 is a very precipitous drop, and then a few of them will make it a long time. So basically, flat and dropped, uniformly dropping, quick and then flat. Okay, so if you look at these two, type 1 and type 3, they're almost like mirror images of each other. Okay, now K-selected species, which invest in their children's survival, they tend to have this type 1 curve. Think about humans. We tend not to die much when we're young, and we get to a certain age, my age, and all of a sudden our odds of not surviving, our odds of surviving goes down very quickly. All right. Compare that to, say, an oyster or some other R-selected species. What happens with them is the vast majority of them do not survive. The initial birth, like as soon as they're born, they get eaten and they die. Okay, because no one's taking care of them. But then those few that do survive, they tend to be able to make it a long time to their maximum age. So it's like a few of them will survive, but those that do are okay. Then you have other things like this is a hydra, but you can also get like birds and squirrels and things like that. Probably mice would probably fall in this category. I've never really looked at a survivorship curve for a mouse, but what we find is you tend to get this sort of constant drop in survivorship as you move through your lifespan. All right, and that's it for survivorship. So we're going to do on our next class, we're going to do a lab where we look at the survivorship of bubbles as a model for different types of organisms. So thanks for watching.